Hey everyone, and welcome to The Explainer. Today, we are getting into something that is absolutely critical for the future of AI, vector databases. We're going to see how this technology is finally giving artificial intelligence something it's been missing, a real, actual memory. So let's just jump right in with a big question, right? You've seen these large language models, LLMs, do some pretty mind-blowing stuff. I mean, they write poetry, they can debug computer code, but then you've also seen them completely make things up, forget what you literally just said 2 seconds ago, or be totally clueless about current events. So what gives? How can something be so smart and so flawed at the same time? Well, this whole paradox really boils down to 3 big problems. First, you've got hallucinations. This is when an AI just confidently invents facts out of thin air. Second, they're stateless, which is a fancy way of saying they have zero memory of your conversation from one question to the next. And finally, they're the knowledge cutoffs. They were trained on data from a while back, so they have no idea what happened in the news yesterday.
Now, these aren't just little quirks. They all point to a much deeper, more fundamental issue. At the end of the day, AI has a massive memory problem. And to fix it, we first have to understand how an AI even begins to process our world.
Okay, so the whole challenge really starts with the data itself. A staggering 80% of the world's information is what we call unstructured. We're talking about text, images, audio, you name it. It's not in nice, neat spreadsheets that computers love. So the first question is, how in the world do you teach a machine to understand the meaning buried inside all of this messy, human stuff? The answer, and this is kind of the secret sauce to all of modern AI, is something called vector embeddings. Think of it as a secret language for machines. Special AI models called embedding models translate all that messy data into long lists of numbers, we call them vectors, that actually capture the original meaning and context. Now, I know it sounds super complex, but the basic idea is actually one you already know. Think about the RGB color on your screen. Any color, like a bright green, can be perfectly described with just 3 numbers, a value for red, a value for green, and a value for blue. Vector embeddings do the exact same thing, but instead of 3 numbers for a color, they use hundreds, sometimes thousands of numbers to describe a complex idea, like a word or an entire picture. And what this does is create this amazing mathematical map of vector space, where distance actually equals meaning. So in this space, the vectors for dog and wolf will be really close together because they're related ideas, right? But the vector for apple will be way off in another neighborhood. This is it. This is how AI begins to understand relationships just by looking at the geometry of these numbers. So we can turn pretty much any data into these meaningful numbers. The next obvious question is, what can we do with them? Well, it turns out this new language completely changes how we find information. Let's look at the old way versus the new way. On the left, you have keyword search. It's rigid. It only looks for exact word matches. You search for cats, you only get cats. But on the right, you have semantic search, which is powered by vectors. It understands your intent. You can search for feline friends, and it knows you want cats. You can search for animals, and it's smart enough to find things about cats and dogs. It is a huge leap from just matching words to actually understanding meaning. But, of course, this new power brings a new problem. Imagine you have a database with billions of these vectors. If your search has to compare itself to every single one to find the closest match, that's what we call a brute force search, and it's just way, way too slow. It would never work for a real-time app. And the solution is a really clever workaround called Approximate Nearest Neighbor Search, or ANN. The idea is simple. Instead of slowly finding the absolute 100% perfect match, ANN algorithms find good enough matches, and they do it at lightning speed. You're trading a tiny, tiny bit of perfect accuracy for a massive boost in performance. It's a trade-off that is totally worth it. So how does ANN work its magic? It's all about something called vector indexing. It's about being smart before you even start searching. The database organizes all the vectors into efficient structures, like clusters or graphs. The best analogy is the index in the back of a textbook. Instead of reading the entire book every time you need to find something, you just look at the index and jump right to the relevant chapter. That's what indexing does. It dramatically shrinks the search space. Okay, let's take a breath. We've figured out how to turn data into meaningful vectors, and we found a super fast way to search through them. Now for the payoff. Let's connect this all back to our original mission, fixing those big, annoying flaws in large language models. And this is where it all comes together. The technique that makes it all happen is called Retrieval-Augmented Generation, or RAG for short. RAG is a system that gives an LLM an open line to an external database, allowing it to look up fresh, relevant facts on the fly before it answers your question. Honestly, this quote just nails it. RAG is like giving the LLM a cheat sheet for an open book exam. Instead of trying to answer based only on what it memorized months or years ago during training, it gets to look up the correct, most current information right at the moment it needs it. So what does this pipeline actually look like? Well, it's a pretty straightforward process. First, your question gets turned into a vector. Second, that vector is used to search the vector database for the most relevant chunks of information. Third, that retrieved info is stuffed into the prompt right alongside your original question. And finally, the LLM uses this new augmented prompt to generate a much smarter fact-based response. And the results of this, they are a total game changer. Because the LLM's answer is now grounded in real retrieved data, those annoying hallucinations are drastically reduced. And since you can update the vector database whenever you want, you've completely solved the knowledge cutoff problem. As you can see, the end result is you get access to current data, which leads to way more accurate and trustworthy answers. You know, this whole RAG approach isn't just a minor tweak, it's a fundamental change in how we're building AI systems. This is the magic behind those customer service bots that can actually find the right answer in a user manual, or research tools that can accurately summarize the very latest findings. And this revolution is powered by a whole ecosystem of new tools. As you can imagine, the market for this technology is just exploding, and it's definitely not a one-size-fits-all world. There are a few different types of tools out there, and each one is built for a different kind of job. We can pretty much break them down into 3 buckets. First, you've got simple vector libraries. These are great for smaller projects where the data doesn't change much. Second, you have traditional databases that have added on vector search features, what we call vector-capable databases. This is a solid choice if you want to add AI capabilities to a system you already use. And finally, you have the heavy hitters, dedicated vector databases. These are built from the ground up for one thing: handling vectors at massive scale and incredible speed. So that's the big picture. We've journeyed from a fundamental flaw in AI all the way to a powerful and elegant solution. To wrap things up, let's just quickly go over the most important things to take away from all this. All right, here's what you really need to remember. 1. Vector embeddings are the universal translator for AI. 2. This allows for semantic search, which is all about meaning, not just keywords. 3. The RAG technique uses this search to give LLMs an external, reliable memory. And finally, and this is the big one, this technology isn't just a nice-to-have. It's quickly becoming the absolute cornerstone of the modern AI stack. And that really brings us to one last big idea to think about. For the very first time, we can give our most powerful AIs a memory that is persistent, that is dynamic, and that is trustworthy. So the question isn't just what can AI do anymore? The really interesting question is, now that AI finally has a memory, what will we choose to ask it to remember? That's all we have for this explainer. Thanks so much for watching, and I hope you have a much clearer picture of the incredible and incredibly important world of vector databases.